To illustrate the application and interpretation of the random effects model, we will use a subset of the famous Grunfeld investment data. This is the same dataset that we used to estimate the fixed effects LSDV and the within estimator. We will discuss the packages and commands in R and Stata that can be used to estimate the one-way and two-way random effects model. The Grunfeld panel data that we will use consists of 200 observations. It has data on 10 U.S. firms from the year 1935 to 1954. The three variables in the dataset include the gross investment of firms over the years, value of the firms, and their stock of capital. The 10 firms included in the data and their coding are shown here. General Motors is coded as ID1, U.S. Steel is 2, followed by General Electric, Chrysler, Atlantic Refining, IBM, Union Oil, Westinghouse, Goodyear, and Diamond Match. The original Grunfeld data had 11 firms, but the one we are using for illustration has 10 firms as it does not include the firm American Steel. Both the one-way and two-way random effects can be easily estimated in software programs like R and Stata. Moreover, the commands are a lot similar to the ones we used to estimate the fixed effects within model. We can use the PLM function provided by the PLM package in R to estimate one-way and two-way random effects model. The command shown here can be used to estimate the one-way random effects model with individual specific effects, similar to the within model we illustrated in the fixed effects tutorial. The results of the model will be saved in the random IND object shown in the command. First, we mention the dependent variable INV and independent variables value and capital. The data option is used to input the name of the dataset that we are using. The effect and model options provided by the PLM function are of special interest to us. The effect option is used to specify whether we want to include individual specific effects, time-specific effects, or both in the model. We specify individual if we only want to include the individual specific effects. Similarly, we can specify time to include only the time-specific effects. Finally, we have the option to specify two ways if we are estimating a two-way model to include both individual and time-specific effects in the model. In the model option we specify random because we are interested in estimating the random effects model. In addition to random, this option allows us to estimate several other models as we discussed in the fixed effects tutorial. For example, we can specify pooling for a pooled OLS model within to estimate the fixed effects within model, specify between for a between effects model, HT for Hausman-Taylor regression, and FD for a first difference model. Since we are estimating a random effects model with individual specific effects or firm specific effects, we will specify model equals random and effect equals individual. For a two-way random effects model, we can simply change the specification to effect equals two ways and everything else can stay the same in the command. In the previous tutorial, we discussed the theory behind estimating the weights theta from the variance of idiosyncratic error and the variance of individual specific random error. We illustrated the Swamy-Arora method, but we also mentioned that there are several other ways to estimate these variances. The option random dot method in the PLM function can be used to specify the method that we want to use for estimating the error variances. By default, the function uses the Swamy-Arora method. Apart from this, we can also specify and use the Walhus, Amamiya, and Nerlov methods to estimate the variances of idiosyncratic and individual or time-specific random error. In Stata, we can use the xtreg function to estimate panel data models. It is also important to note that we must declare the dataset to be a panel data using the xtset command shown here. The syntax for this command is xtset followed by the ID identifier and time identifier. Therefore, we input xtset firm year in our Grunfeld example. In the xtreg command shown here, we first mention the dependent and independent variables as usual. Then, we just have to specify the option RE at the end to estimate the random effects model. This command will automatically include the individual specific effects or firm-specific effects in our example. However, to include time-specific effects, we must use the I.year term like we did in the fixed effects approach. Stata does not provide the option to include time-specific random effects in the RE option of xtreg command. As a result, we have to include time dummies to account for the time-specific heterogeneity, that is, we can include time-specific fixed effects only. The option theta can be used to report the weights theta. It is important to note here that theta will be a single value in balanced panel data, that is, when all the individual units have data on same number of time periods. However, in case of unbalanced panels where observations may be missing for some units in certain time periods, theta will report the minimum, maximum, quartiles and median of the weights matrix. This is also evident in the theta formula we discussed in the previous tutorial. As we can see, number of periods Ti will be the same for all units in a balanced panel. Hence, theta will be the same for all units I, that is, a same or single value. But, the weights theta will end up being different for different units in unbalanced panels because the number of time periods Ti might be different. The option SA can be used to estimate the random effects model using the small sample adjustment of the Swamy-Arora method. By default, the usual Swamy-Arora method that we illustrated is used to estimate random effects. However, the SA option can be specified in case of small samples. In addition to the random effects model using the RE option, the xtreg command allows us to estimate several other models. Instead of RE, we can specify BE for a between effects model, FE for fixed effects within model, and PA for a population averaged model. Moreover, we can also estimate the random effects model with maximum likelihood estimator using the MLE option instead of RE. Now, let us take a look at the results of the random effects model. The table here shows the coefficients and other statistics that are usually reported in the random effects model. The coefficient associated with the value of the firm is 0.109781 and that of capital stock is 0.308113. Both the coefficients are statistically significant at 1% level. The interpretation of the coefficients is straightforward at this point. With 1 unit increase in the value of a firm, gross investment increases by approximately 0.110 units. Since the data is in millions of dollars, we can say that with 1 million increase in value, gross investment of a firm increases by about $110,000. Similarly, with 1 million increase in capital stock, gross investment of a firm increases by about $308,000. Hence, the interpretation of coefficients is similar to OLS and fixed effects models. For instance, if all the variables were transformed using natural logarithm, then we could interpret the coefficients in terms of approximate elasticities. In addition to the coefficients and their standard errors and p-values, we are also interested in the estimated error variances and some other statistics. The estimated variance of the idiosyncratic error is 2784.46 and its standard deviation is 52.77. More importantly, the estimated variance of the individual specific random error is 7089.80 and its standard deviation is 84.20. This is a strong indication that the individual specific effects are relevant. This is because its share, sometimes estimated as ρ, is 0.718 or 71.8% out of the total variation in the error. The weight theta is equal to 0.8612, which is a single value in a balanced panel. We may have a weight matrix theta in case of unbalanced panels because of different number of time periods for different units. In that case, the results will usually report the minimum, maximum, mean, median and quartiles of theta matrix. If we want to look at the weights theta in R, we can do so using the rcomp function provided by the PLM package. This function can be used to estimate the variance components of the panel data models. Moreover, it also stores the weights theta, which we can easily access using the commands shown here. This theta will be a single value in case of balanced panels, like our example. However, if we are dealing with unbalanced panel data, then it will report the theta matrix with different weights for each individual unit. The chi-square test shown here is applied to test the overall significance of the model. The p-value is less than 0.05 and even less than 0.01, indicating that the independent variables are significantly improving the fit of the model. This is expected because the coefficients of both the independent variables were significant as well. If we compare the estimated coefficients of this random effects model with the fixed effects within model, we notice that the coefficients are quite similar. In our example, this happens because the theta is 0.8612, which is close to 1. Remember that the random effects model reduces to a fixed effects within model if theta is equal to 1, as we discussed in the previous tutorial. Since theta is quite close to 1, the coefficients are also close to the coefficients of within model. If theta is 0, then the random effects model reduces to a pooled OLS model. Therefore, theta being as high as 0.8612 is a strong indication that the random effects model is appropriate as compared to pooled OLS. Whether we should prefer random effects, fixed effects or pooled OLS model, we will discuss this in more detail in the next tutorial along with appropriate goodness of fit tests. To obtain the random effects or individual-specific random errors after applying the random effects model, we can use the runif function provided by PLM package in R. As shown in the command here, we input the random IND object containing the results of our random effects model. Next, we specify individual in the effects option because we want the individual-specific random effects. If our model contains time-specific effects, then we can specify effect equals time to obtain the time-specific random effects. In a two-way random effects model, we have to specify effect as individual and time separately in different commands to extract the individual and time random effects one by one. In Stata, we can use the predict command to obtain the random effects. In our example with individual-specific random effects, we can use predict UIU as shown here. Here, UI is simply the name of the object in which we want to store the individual-specific random effects. In our example, the individual-specific random effects as estimated by our model are shown in the table here. Hence, each firm in our example has its own estimated random deviation from the constant. If we include time-specific effects, then each time period will have its own random error. In a two-way model, each individual unit and each time period has a random deviation from the constant that can be estimated as error terms in the random effects model. Thank you for watching, and I will see you in the next tutorial.